Hi friends, welcome back to our channel. So in this video we will see how to configure timer peripheral. So what is the importance of timer peripheral? So if you want to start counting, right, count certain event or what is the duration of certain event, to calculate that time difference, we need the timer. Timer basically is like a clock. We are counting certain clock ticks, how much time has been lapsed between two events, that we calculate using timer. Now we will start with our programming, right? We will copy our previous code and we will paste it over here, and we will rename it as a timer. We will rename it as timer. So this is our sixth tutorial in bare metal programming. We will rename it as timer and we will close the previous project. Now we have all the files. If you go into main.c, right, we have gpio.h also, we have main.h also, and in main.h we have rcc base, rcc, right, and edc peripheral. Now for our timer tutorial we don't need edc, so rest of this thing we will delete and we will write a clean code. We will write a clean code. First we will try to understand what is the timer peripheral, how it can be configured, and what is the use of timer peripheral. What are the importance of timer configuration or timer peripheral? So let's suppose I'm getting one pulse, logic pulse between this, and that event is occurring after some time, that event is occurring again. So I want to calculate the time duration between these two pulses on the same GPIO pin. So for this I can use timer peripheral. If I want to calculate frequency, this is classic example. If I want to calculate frequency, then I'll need timer. Timer peripheral can be also used as a counter. So how many pulses have occurred on GPIO pin during 1 second, that we can calculate using timer or counter, and inverse of that we'll take as a frequency, right? So we can use timer as a counter also. So there are multiple uses. How does the timer peripheral work? So in race what happens is, when a player starts running from the start line, we start the clock. Okay. So let's say t0 duration, and after that when he crosses 100 meters we stop our clock. So we have a clock. Now we know that this clock is in seconds and precise in microseconds, right? So whenever we click the stop button, right, whatever value, it will be displayed. So we know the time period of this. This will be, let's consider that this is 1 microsecond, and how many clock cycles have occurred during this interval. We can calculate those, we can keep a count of those, and once we get the count, let's suppose n into 1 microsecond, right, we get n microseconds. Now we know that, right, if I divide this n microseconds by 1000 first, we will get millisecond, and if I again divide this whole value by again 1000, I get seconds. Now I get the seconds value, right? 60 seconds means 1 minute. I can easily convert this. Now I can divide this whole thing by 60 and I can get the minutes value. So why I was giving this example? So we give a timer base or clock base, and depending on how many clocks have been elapsed during occurrence between two events, those number of clocks we calculate. What is the count of that clocks elapsed, that we calculate, and according to that we calculate our time, that how much time has been elapsed. Now to configure the timer peripheral we will need the base clock. So we know that our controller, right, STM32 F401 CCU6, it has internal 8 megahertz RC clock. till now, till our tutorial, we have not configured this clock. We have kept it as default, right? So this is our system clock, 8 megahertz of 8 megahertz. We'll go into our datasheet. We'll see one by one how we can configure the timer peripheral, and from there we will get a good picture, right? Good idea how we can configure the timer peripheral. So we'll first go into datasheet. So from the datasheet we will see which modes we can configure for our timer. So what is the maximum value that we can load? What is the timer base that we can select? These all things we will see from the datasheet. We have advanced control timer, timer 1, timer 2, timer 5, timer 3, 4, right? 9, 10, 11. These are the timers that we have, right? Timer 1 is of 16 bit. We can configure it as up down counter, right? Up down counter type, any integer value between 1 to 65535. So, and maximum clock frequency that we can give is 84 megahertz for our STM32 F401 CCU6 microcontroller. So from here we can see that we can configure our timer 1 in 16 bit resolution. So 2 raised to 16 is 65536. So that is the prescaler value. We can again configure our timer in up down or up down counting mode, right? We have compare capture, 4 channels for compare capture mode. Then we have complementary output, and we can give 84 megahertz of maximum clock frequency to our timer peripheral, right? If you go for timer 2, timer 5, we have 32 bit resolution. So 2 raised to 32, that many number of that is the maximum value that we can have. Then we have up down counting mode, right? We have DMA request. We have 4 capture and compare channels. Then we don't have complementary output on timer 2 and timer 5. The maximum clock frequency that we can give is 42, right? And timer clock that we can have is 84. Now this is multiplier basically. We'll see that into the next part, right? So this is an overall picture like how we can configure the timers in different modes. Now comes the advanced timers. There are advanced timers and there are general purpose timers. We will be configuring in general purpose timers. So this is the brief introduction about the general purpose timers. I won't go in detail. So we have 16 bit auto reload up down counter, 16 bit prescaler, right? Then we have PWM, 1 pulse mode output. We have capture compare, output compare, right? So this functionality we have on timer peripheral. Now we will go into the user manual. We will go into the user manual. Obviously we will need the RCC register. Timer 2 and timer 5 for this tutorial. It is a 32 bit auto reload up down counter with a 16 bit prescaler. So from user manual we will get in detail information. So as we have spoken earlier in previous videos also, in previous tutorial videos also, that before configuring any register of that peripheral, we need to enable the peripheral clock. Without that we cannot configure any bit of that peripheral register, right? So in our case, if we do not enable the timer peripheral clock, right, we cannot configure the timer registers. So for that we will need RCC register. So we'll come into the datasheet. We'll go into the memory map. Here we will see where the timer 2 peripheral is connected, like to which bus it is connected, what is the base address, right? That information we will get from datasheet. So let's see. Our interest is of timer 2. So we will see timer 2, right? Now timer 2, here it is. The base address of timer 2 is 0x4000. So 4000 and it is connected to APB1 bus. So we'll make a note of that. Timer 2, the base address, it is 0x4000 and it is connected to APB1 bus, right? So it is connected to APB1 bus. So this is the base address. So why we noted down this address? Because from our timer 2 registers, right, we'll start from this address. So that's why we noted it down. It is connected to APB1 bus. So what is the importance of APB1 bus? Timer 2 is connected to APB1 bus. So what we'll have to do is, we'll have to go into RCC APB1, because timer 2 is connected to APB1 bus, and enable registers. So that's why we have noted it down. So if you want to enable the clock for timer 2 peripheral, we will have to go into RCC APB1 ENR. So we will go into RCC APB1 ENR. So here it is, RCC APB1 peripheral clock enable registers. Now our interest is of timer 2. It is at bit number 0. To enable the timer 2 peripheral, we'll have to set bit number 0. Right? To enable timer 2 peripheral clock, we'll have to write 1 to bit number 0. So let's make a note of that into our code. Now here what we'll do is hash define RCC APB1 ENR. Right. Now we'll give it a pointer uint32 underscore t pointer RCC base address plus, let's check the offset. What is the offset of this register RCC APB1 ENR? The offset is 40. Address offset is 40. 0x40. In order to configure timer 2, first we'll have to enable the peripheral clock of timer 2. So what we'll need to do is RCC APB1 ENR. This is a pointer, so we'll have to dereference it. Now equals to, right, we have to set bit number 0. So 1U, let's bit num 0. So why we have done like this? So what the value of this bit number 0 macro is 0. The value 1U shifted by 0 times, it will be at bit number 0 itself. Okay, so it simplifies the code. As we go on progressing, right, we will add all these bits from bit number 1 to 15. Okay, so 1 2 3 4 5 6, and here we will modify 1 2 3 4 5 and 6. Easy for debugging also. 7 8 9 10 11 12 13 14 and 15. So 15 14 13 12 11 10 9 8 7. We have total 32 bits, right? So we can go and define all those bits. So what I'll do is I'll copy over here, paste it over here. 16 17 sorry 18 19 20 21 22 23 24 25 26 27 29 30 31. Right, so you might modify this as 30 29 28 27 26 25 24 23 22 21 20 19 18 17 and 16. So now we have declared the bit position. Why we have done like this? To simplify our code writing, so to make our code easy for understanding and easy to clean. Now we have enabled the timer peripheral clock. That was our first goal. First timer, first thing हमारा जो था timer peripheral clock enable, right? This we have done. So now again we will go back into our user manual. Here we will go into our timer sections. So we have enabled the peripheral clock. We are not using GPIO, or we are not using ADC peripheral. Basic timer, general purpose timer. So here you can see timer 2 and timer 5. One more important thing to discuss over here is we are not using timer on any GPIO port pin. So not using timer on any GPIO pin. So there will be no hardware signal that will be provided on any GPIO pin. The timer will be for internal use only. So it will be used internally inside the controller. So that's why no alternate functionality has to be set, and that's why no GPIO peripheral clock has to be enabled. Simple as that. Now we'll go into the timer section. See, we have 16-bit or 32-bit auto reload counter. Now see, we will go into the main features, right? Timer 2 is of 32 bits up down auto reload counter. It has 16-bit programmable prescaler. Now it has 4 independent channels, up to 4 independent channels. It can be configured as input capture, output compare, PWM generation, 1 pulse mode output. Again, interrupt out DMA generation events, it can be used, update, counter overflow, underflow, then counter initialization by software external trigger events to generate the trigger events, counter stop, initialization, input capture, output compare. So for all these things, we can use the timer too. Now let's go inside general purpose timers. If you see this diagram, you will feel like, oh, what a big diagram. But don't fear, okay? And this is very simple diagram. This is timer channels, then which timer has to be selected, which timer input FP1, or which prescalers, how prescalers should be selected, where is the counter, what is the output control flow. Then here you can see that internal clock, then interrupts. So all these things will be used one by one we'll see, but for this tutorial we'll keep it very simple. As we progress, we'll definitely use the advanced functionality of timer. So whatever code explanation I'm giving, it is for the basic level, okay? Now timer 2 functional description. We have counter registers, then we have prescaler registers, then we have auto reload register. These are important things. Auto reload is preloaded. Then timer 1 control registers, then UEV update event, so clock count. So all these registers are there. See, now prescaler definition is given here. A prescaler can divide the counter clock frequency by any factor between 1 to 65536, and it is based on 16-bit counter controlled by 16-bit or 32-bit register. Timer 1 prescaler, PSC means prescaler. Now see, I'll just explain it. I'll try to explain it as simple as possible. Now this is our timer peripheral. Now it will have clock input. So it will have clock input. But at times what happens is, we don't want the fast clock. We want our timer to be very slow, because this controller clock, if we have seen, it is 42 megahertz, or maximum that we can give is 84 megahertz. So if we invert, even if we invert 1 megahertz, we get one clock period of 1 microsecond, right? And obviously divided by 84, that will be the period for this 84 megahertz. And we don't want that much fast clock. If I calculate using this 1 microsecond clock, so it will be a huge headache to measure it continuously, right? So for that, what we have inside this timer peripheral, we have a clock divider. It is known as prescaler. So whatever input clock we get, it divides that clock. If we use a prescaler of 2, then after every 2 clock cycles we'll get the clock. So if we use a prescaler of 2, right, then this is our clock. So this is our input clock. If you use a prescaler, that will then we'll get the output of prescaler output of like this. Clock input will get divided by 2. Now this clock will be used as a timer input clock. So this is our input peripheral clock. So clock in will go to the peripheral prescaler block, and after dividing that clock, it will go to the timer. It will be passed further, okay? So see, it is given like this. This is our clock. This is prescaler clock. See, if it is changed from 1 to 2, you can see here timer counter was incrementing each clock, but after using the prescaler of 2, after every 2 clock, it is incremented by 1. So this happens. This is the importance of prescaler. The clocks or the counter slows, timer slows. So what we will do is, see, the description is given. If we increment the prescaler from 1 to 4, the timer was counting, or the timer was incrementing after each clock. But after changing the prescaler from 1 to 4, the timer value is incrementing after 4 clocks. That is the importance. So we will come to up counting mode and down counting mode. So in up counting, what happens is, we can start counting from particular value and we can increment that count. or the counter increments by 1 in up counting mode, and in down counting mode it decrements by 1 from particular value. So in up counting, the example is given like from 31 it will go to 32, 33, 34, 35, 36 likewise, and from 0 it will increment to 1, 2, 3, 4, 5, 6, 7, 8 likewise. In down counting mode, what will happen is it will decrement the value. So from, let's take example of like 32, it will down count to 31, 30, 29 likewise. Okay, so from 10 it will count to 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. After 0 it will again go back to the auto reload value and it will start down counting from that value. In up counting, what will happen is it will start counting, it will reach till the auto reload value, and once it matches with the auto reload value it will again start counting from 0. Okay, now will come, these are center aligned modes and everything. Then the clock selection, this is internal clock. What is the internal clock we will have? So for this tutorial we are going to use an internal clock. We are not going to use any external event for which we want to calculate, or we don't want to calculate any frequency, any counter. So we are just simply going to configure one timer of, let's take 5 seconds. After 5 seconds we'll precisely generate delay, toggle the LED after 5 seconds. So we'll toggle the LED on that update event. So internal clock source we will use. We are not going to use input capture, output capture, forced output mode, output compare mode. So we are just simply going to use an timer mode. So the goal is like configure the timer, configure it such that after every 5 seconds there will be an update event, and at that update event we will toggle the LED. Simple as that. Now we will come to the timer registers. We'll click on bare metal, click on file, click over here, include, and we'll give the name as timer.h, right? Then we'll provide if and def timer underscore h underscore, then hash define, and then we'll use end if. Then we'll use hash include std int.h. Now first thing we will do is type def struct timer. We can simply give the name over here, timer reg def underscore t. Okay, and we can give hash define timer2 base addr base address. We have seen the base address for the timer, it is 40000000. Now we will come to the register map. So first we will check the register map. What are the registers into timer peripheral? So it is CR1, CR2, SMCR. So we will make it volatile uint32 because each register is of 32. CR1. Now we'll copy it 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Then we have CR2. Then we have SMCR. Then DIER, SR, EGR, DIER, SR, EGR. First we'll write it down all the things and then we'll check, explore. CCMR1, it is at 18. CCMR2, CCER, CCMR2, CCER, CNT, PSC, CNT, PSC, it is Prescaler, ARR, then one is reserved, ARR, reserved 0. Okay, if it is not volatile, that's fine because we are not going to use that. Right? CCR1, CCR2, CCR3, CCR4, CCR 1, 2, 3, 4. Right? I can write it like the array of CCR registers. Then again one result, then DCR DMAR, no, DCR DMAR, OR and OR. OR is simple, OR. So we have the last register is OR, right? So these many registers we have inside the timer peripheral. I'm not going to write the offset for each of the registers because I have explained it in previous videos. I'm not going to explain it again here. Okay. We are going to see the registers and which registers we need to configure, right? So the register definition we have declared. Now we'll go into main.c. First we need one timer. So what we will do is timer regdef, right? Timer regdef will take timer2. We need a timer2 pointer. So what we will do is regdef pointer and we'll take the base address, timer2 base address, because we are configuring timer2, that's why. So if you want to configure timer5, you will have to declare the timer5 base address, and in main.c you will have to use timer5 base address. Because I'm using timer2, that's why I'm over here I'm using timer5. So we'll note it here, we are using timer2 peripheral. So here we have timer2 peripheral clock enable. We have done this, we have completed this. Now in timer2 peripheral we are going to use internal clock. We are not using any external. We will be using up counting mode. We will see prescaler, we'll calculate the prescaler, then we will check the value for auto reload register, the initial counter value that we'll see, and then we will enable the timer. This will be the things that we'll see. Okay, one more use of timer peripheral is that we can generate precise delays. I'm again repeating, one more important use of timer peripheral is that we can use timers to generate precise delays. This is use of timer peripheral. Okay, now we'll see these registers one by one. A good example is that, like, we set the alarm clock. Alarm clock is totally a different concept, but yes, just I'm telling you that one good example is of like alarm clock. We set like 10 minutes timer. After 10 minutes or after half an hour we need to check something. So for that we set the timer of 30 minutes, we set the timer of 1 hour, we set the timer of 15 minutes, right? Likewise. So what happens in background is there is a timer clock. So on that timer clock, precise timer clock or 1 second clock delay, it is counted, and once it reaches the 15 minutes delay, an event is generated. That event is like sound, beep sound or alarm sound. So you get the alert. Okay, 15 minutes has elapsed or 1 hour has elapsed. So that is the use of timer, right, to generate the precise delays. Now we'll come over here. So we'll go one by one. We'll come over here and we'll go into the first register is control register. Now if you see clock division, the division ratio of timer clock frequency and sampling clock. So we are not interested here because we want to keep the tutorial simple as that, right? Auto preload register, ARPE. So we'll see for that. Center align mode, right? Center edge align. The counter counts up or down depending on the direction bit. It is 0 0. So if we check the reset value is for the all bits is 0 0. So we'll keep it like that. The direction register. Now this is important. Which direction we want to do? We want to do up counting or we want to do a down counting? So let's keep up counting. So it is 0. By default it is 0. If we want to change it to down counting, we will make it down count by setting this DIR bit. Okay. So for now it is up counting. Then one pulse mode. Counter is stopped at update event. Counter stops counting at next update event, right? Update event we want, right? Update request, then counter overflow. If 0, right? If this URS bit, update request bit, it is set to 0, that any of the following events generate an update interrupt or DMA. We have not enabled the interrupt, that's why it will do only set the flag and it will go for like count next counting. Okay, then setting the update generation bit, UG bit. Okay, only counter overflow underflow generates an update interval. So let's keep it simple. Let's keep this bit as 0. The default value is 0, so we are not going to set it. Then update disable. If this UDIS bit is set, then update event is enabled. Which are the update events? Then counter overflow, setting UG bit, update generation through slave mode controller. If it is set to 1, then update events are disabled. So we are keeping it 0 for now. Then counter enable. So over here, if we write it 1, then our counter is enabled. So this we will have to do after configuring everything. So this bit we have to set at the last, right? Counter enable bit. So enable the timer. What we will do is Timer2. Now this is in CR, right? CR1. The last bit we want to set. So 1U and bit number 0. Now this will enable the timer.